Welcome to this second lecture on TCP-IP networking. We left last week with some considerations on timing. We will continue a bit of those today. We will see the implications they may have on protocol design. Then we'll dive into the first big piece of our menu, which is the IP layer. This is where we left, more or less, last time, about the consideration that propagation, though very fast, might not be negligible when we go long distances. The bit rate, often called bandwidth, is the bits per second that a physical medium can transport. Ethernet today, the basic Ethernet cables are at 100 megabit per second for most of them. Another closely related concept is that of throughput. So what is the throughput? The throughput is the useful thing you get out of the network. It's also measured in bits per second. If you are alone on a cable transferring data between a client and a server, and the cable is at 100 megabit per second, perhaps you will get a throughput close to 100 megabit per second. In fact, you will get less because of protocol overhead in order to transfer some information, as we will see when we analyze IP and all the layers. Each layer adds some overhead. So in order to send one bit, we need to add, for example, in the case of IPv4, 20 bytes. So that will eat up some of the throughput. So usually the throughput is 10–20% less than the max possible. Plus, there are typically inefficiencies due to waiting times, competition. We will come back to those when it comes to sharing an internet infrastructure. If you're not alone, but there are 1,000 like you sharing this 100 megabit per second Ethernet cable, obviously you might get much, much less than 100 megabit per second. But even if you're alone, you might get much less because of inefficiencies due to timings. Here is one type of inefficiencies. The stop-and-go protocol. That's our first non-trivial protocol. The stop-and-go protocol is a protocol you implement in the application layer when you use UDP, for example, when you use an unreliable transport. The idea is you send a message from one source to a destination. Then, since you're not using a reliable transport, you want to have an acknowledgement, either explicit in the case of DNS, for example, or in the case of the stop-and-go protocol, or often implicit if the logic of the application requires a response to be sent. And then once you have received this response, you can continue. Assume we do this for transferring data. So you want to transfer a file from A to B, and you use that protocol. You send one block of data, you wait for the destination to acknowledge, then you send the next one, etc. That is what is done, for example, when you have very simple things. That is what is done locally between, for example, two pieces of hardware in a computer. And it's called the stop-and-go protocol. Why is it called stop-and-go? Because essentially, when you finish sending, you stop until you receive a release message, which is the acknowledgement that lets you go again. Let's do a performance analysis of this protocol. Here I'm showing, as usual, a space and time diagram, where here time is flowing horizontally. I'm showing the A, that's the source, and B, that's the destination. So the red time here is the time to transfer a block of data, one IP packet, for example. The time it takes is dictated by the bit rate of the channel. Here I'm assuming in this academic example that I have one channel with a well-defined bit rate, which is what you have if you're alone on your cable. It might be otherwise the average capacity you get from sharing a path in the internet. That, I'm assuming, takes the same time at the receiver, which is usually what happens. The receiver gets the packet, builds an acknowledgement, and sends it back. And at this point, the acknowledgement has arrived at the receiver, at the source, and the source can send another packet. What is the throughput of this protocol? Or what is the efficiency? Efficiency is the ratio between the throughput and the channel bit rate, which is the quantity B here. Well, it's easy to do if we assume there is no loss, which I'm doing here for simplicity. I can observe that a system like this goes by cycle, where I send, I wait until I receive the ACK, and I continue sending. In one cycle, how much useful data did I send? So in one cycle, which has a certain duration, I have sent the red data. So I have sent an amount of data, which is here coined capital L, the size of the packet in bits. And what is the cycle duration? The cycle duration is the time to transmit the data, which I call capital T. The propagation time, which is the two-way propagation time, the time for the first bit of my packet to reach the destination, and for the first bit of the acknowledgement to reach me. I'm assuming it's the same in both directions, which is often true, but not always. Here I call it 2D. And then also the time to receive the acknowledgement. So that's the total cycle time. What's the throughput? Well, the throughput is if I do a very long run, I have a large number of cycles. In every cycle, I have L bits or bytes that are being sent. Every cycle has a certain duration. So the average throughput is L, the number of bits, divided by the duration of one cycle. If we do the math, we will find therefore this. And by pretty printing it, we find that it is equal to B, the bit rate. Take my professor stick. B, the bit rate, divided by this denominator that's larger than 1, which captures the inefficiency. And we see that the inefficiency has two terms. First, it is the ratio of the acknowledgement to the data itself. We can count that as overhead. In order for the protocol to work, we need to add information which is not the file we're transferring, but is overhead information. So that is something we will always pay for. And then there's another thing here, which is 2 times dB divided by L. 2D is the round trip time. B is the bit rate, bits per second times seconds. This is in bits, relative to L, the number of bits or bytes we are transmitting, the useful bytes. This is called the bandwidth delay product. So it's not the total thing, but this is slightly incorrect. The circle should be this is the bandwidth delay product, because people call B the bandwidth and delay is 2D. It can be interpreted as follows. I have a bit rate of, for example, 100 megabit per second. If I have a delay of 1 second, that means that it takes, when I send data, the data that are on the fly, the ones that are here, that are being sent and not yet received, namely the data that are in the wires or in the radio channels, is exactly measured in bits, is the bandwidth delay product. So those are the data that are flying on the internet. Of course, those are data you cannot stop. Once you have sent them, you cannot stop them. And those are data essentially you don't control. And we see that the throughput is in fact largely influenced by those two terms, the efficiency of the protocol. You try to make it as efficient as possible by sending large blocks of data, for example, if you have a large file to transfer, so that the overhead will be small compared to the useful data. This you can control by your protocol. And something that you don't control, which is the bandwidth delay product. Here are a few numbers for the few examples we studied last time. We have looked at 4 different ratios of transmission and propagation time. And we find that in one case, for example, when we send data at a reasonable rate, 1 megabit per second, it's probably the best we can get today over the internet. But long distance, then we see that the throughput of this protocol is less than 4% of the bit rate that I would have on this channel here, which means most of the time with this protocol, I'm waiting for data. So if I send, wait for acknowledgement, and send again, with a protocol like this one, most of the time they're waiting. So it's largely inefficient if your goal is to transfer the data fast. In all other cases, they perform fairly well. So this is one of the issues that TCP has to solve. TCP is about doing for the programmer a solution that would fit all cases. So TCP has to provide error recovery, so it has to send acknowledgement and know whether a packet is lost or not. So TCP will have to work in all of those cases. Working in this case is easy because even a very primitive protocol will work. Working in this one, as we will see, will require what is called a sliding window that we will see a bit later. So that illustrates already when you're doing your own application layer, if you are doing something simple, like you send one ping and wait for the response and that's it, then probably you're happy with the stop and go protocol. If doing something that involves a larger amount of data, perhaps you will need to think and do something smarter that will avoid this blocking by pipelining, typically. We will come back to this when we will study TCP. That will explain a lot of the complexity of TCP, the sliding window in particular. To conclude on this part, I would like to put things together, and this is perhaps a summary of things you could observe in Lab 1. So here I'm showing a very small network with an Ethernet part, a wired part on the right, and a wireless part on the left. And I'm showing a web server that's sending data to a mobile device, to LAN here. And we observe the data at different pieces of this chain. Here is, I would say, academic view or a layered view of what is happening. Here I'm showing the three main elements in this exchange, the two computers, the server and the client, and the router in the middle. The first thing that is worth keeping in mind is the application and the transport layer are, in principle, not involved in the router. That's the goal of packet switching as opposed to store and forward. So the router will involve only the IP layer and the layer below. Let's do a small animation of what happens when the application program, for example, the web server, sends a block of data to the client application. It will call something like this, if this is in the syntax of the socket application programming interface that we will exercise in Lab 3. So the server sends a block of data. The transport protocol takes this block of data, chops it into as many packets as is required. The packets have a maximum size, which is not too large. If it's a photo that doesn't fit in one, then it will be broken, for example, in 5 pieces. Then each of those pieces has to be transported as an independent IP packet, 5 postcards, if you want. So this will be done by adding to each of those 5 pieces an IP header, which contains essentially the source and destination IP address. And then we transmit that to whom? Well, to the next router. How do we transmit to the next router? Well, because we're connected in this part of the network by Ethernet, we transport it by Ethernet, which involves adding to the IP layer the Ethernet header, which contains essentially also addresses, MAC address of the router and MAC source address of this server, which is shown here as the red header. Now this is transformed by whatever Ethernet version you're using into physical layer signal. The packet is received by the router because it contains the destination MAC address of the router. The router does its job as a router. What's the job of a router? A router is a letterbox or a switching system of the IP layer. That means it receives IP layer, reads the destination address, and sends them to the destination or to the next router, like a post office switching system does. So it first needs to receive the IP packet, which means removing the Ethernet header and looking at what's inside, which is, for the router, in principle, is only the IP header. I say in principle because, of course, since a router is essentially a computer, a special purpose computer, it can look at every field of the packet. But in principle, it should not. It's important to know two things here. It's important to know what things should be, but it's important also to see how they are in practice when they are not as they should be. We will see an example later today of a router or something called a NAT that does a few weird things. But it's much easier to understand things if you know what is the rule and what is the exception, rather than having a flat descriptions of all the things that happen. So the rule for a router is it looks only at the IP header. In the IP header, there is the address of Elaine's computer on the left here. So it will analyze the IP address. It will discover from the IP address that it has to send it over the wireless LAN directly to Elaine. How does it do it here? Because of the subnet mask. The computer knows the subnet mask of its wireless interface here. It analyzes the destination address that's contained here, and by analyzing this, it knows that the destination address is on the same subnet. Therefore, I send it directly. Sending directly means putting a MAC layer header, which is now not the same as here, is a Wi-Fi header, which is practically the same as Ethernet with one or two minor differences. But the main difference is now the MAC layer destination address is the address of this machine here. Then the packets will be transmitted. The destination will copy them because it will recognize its own MAC address. It will pass it to the software. Typically, this is done in hardware. This is done in software. We'll pass it to the software, to the IP layer, that will analyze the IP destination address. In principle, it should be the IP destination address of this machine. If not, and you're not a hacker, then you drop the packet. If you're a sniffer, that might be on purpose. But in principle, that should not happen. It's an error case. And then the network layer passes it to the transport layer under the assumption that there is somebody listening and ready to receive this, which is probably what has happened, because if the web server sending data to Elaine, it is because Elaine has already contacted the web server. So this data is put in what is called a socket queue, socket buffer, and hopefully sometime the web browser will issue a read on this socket buffer and we'll be able to receive the data. Voilà, that's one single cartoon animation of how the internet works. Some terminology. Every layer creates packets in some kind. At every layer, they have different names. The packets created by TCP are called segments, TCP segments. The one created by IP are called packets per se. The packets of the Ethernet layer are called frames. And in general, you might find verbose papers that use those terminology. I will not use very much, but it might be, it might hamper you if you don't know it. So in general, when we have two entities at the same layer that are communicated, for example, TCP or IP, what they do between each other is the protocol. This we have mentioned already. The data that they generate and send to each other is called the PDU, Protocol Data Unit. And the data that they issue to the upper layer is called an SDU, Service Data Unit. So here the important keywords are the protocol is between two peer entities. So the TCP protocol, TCP is a protocol between two transport layer entities. The service interface is how you use this layer. So the TCP service interface is the socket layer, for example. Voilà, for the terminology. Another way to look at it is sometimes called the onion view. That's what we see when we do Wireshark or TCP dump. We see, now if we sniff the packet, for example, on an Ethernet cable here or on a Wi-Fi, if it's not encrypted, we will see a MAC layer packet, which contains a MAC header and a MAC payload. The MAC header, again, contains essentially addressing information of the MAC layer. What is the MAC payload? Well, the MAC payload is itself an IP packet, which itself contains an IP header, an IP payload, and the IP payload itself contains a TCP header and a TCP payload. In principle, the TCP payload contains the application layer, for example, the bytes of an HTML file. But as we will see later, again, this is software, so everything is possible. You can easily imagine putting things in a different order. For example, you can put an IP packet inside a TCP segment, or you can put a MAC layer packet inside an IP packet. All those things can happen. Again, there are deviations. They should not be done in principle, so we will see exactly when and how this is done. This is how you can print it when you use Wireshark or similar things. You've done that in principle in the lab. So now let me ask you a little question to verify if the lab was useful. Here is Wireshark we're doing here. So it's the same scenario as before. The web server is sending information to Elaine's mobile device. We observe a packet here with Wireshark, say what is true about destination addresses. Yes? Is one between the router and the client? Yes. So this is the Ethernet concentrator, the cabling system. This is the router, and not shown here on the left, there is the wireless part. Next week, we will have a test on Friday that will have 10 questions like this. So it's a good training. The grading scheme is there are 4 possible answers. Exactly one of them is true, because we, in the past, used clickers, and the only way to use clickers in a reasonable way is to have one possible solution. And there is a don't know, which means in the test, if you don't tick any box. The grading is, if you have the correct answer, you have +1 point. If you have a wrong answer, you will have -1/3. Why -1/3? Because there are 3 negative alternatives. So a robot that plays at random will have an average 0. I close the poll. So the majority, this is unimportant. It's very easy, but very important. So it's important to have this correct before you continue. So this packet is sent by the web server to Elaine. So what should the web server do? Well, it should analyze the IP destination address and know, what do I do with this packet? Oh, I have to send it to the router. Sending it to the router, seen from the IP layer, means sending it via Ethernet to the router. The only way to do that is to put as MAC address, the MAC address of the router. Therefore, the destination MAC address should be the MAC address of the router. Now, the IP destination address should be, of course, the IP destination address of Elaine. That's the principle of the IP network layer. You send to someone by putting the address of that someone you're sending to. So the correct answer is the majority vote, which is this one. And that's easy but important. So most of you have that correct. If you don't, it's time to correct your thinking. And that is the end of this introductory part. Questions?